Good. Today's lecture is actually this is our last topic that we have, and maybe I'll repeat some things we already went through, but they will be in the context of reuse. So now actually. Reuse is a kind of an aspect in its own right. This is not saying too much, yeah, reuse, but when we say reuse, what comes, at least to my mind, I don't know about you, might disagree, comes to my mind are components. It's like in other fields as well, like in electronics. You have electronic components and you put them together and you have electronic devices. And those components there are generic enough to be composed into different settings, different devices, and you don't have to build your own components normally. So you're not working on that level. You just buy those that satisfy your needs. Have you opened any of the devices, by the way, that you use, electronic devices? And we managed to identify which component is what kind. I know there are different kinds of those electronic. Typically, resistors were marked with some circles, some color, and so on. It was some time ago. But even if you would open an older TV, really old TV set, you might find some. I don't know. You might identify what they are approximately, but there are no marks there. So some components, even electronic components, are developed specifically for the purposes of that particular device. So that analogy, that dream that we often dream in software development, putting together, having some components, some generic components, and some component market, and then just go there and pick up the relevant components and put them together is not really, doesn't have analogy even not even in full analogy, not even in those more harder fields, not just electronic components, but all kind of mechanical components, whatever. So the devices that are being developed need to satisfy some limitations. So you need them to be small or waterproof or whatever. Or I don't know. They need to satisfy some serious limitations, and those generic components would not even fit if you just imagine the conventional size. You could not have smartphones if you would not develop your own components adapted to your needs. Yet there are lines of products that are based on the same components. So quite similar. Nokia was quite good at this, and they produced lots of similar smartphones or phones in general, and they used similar components to put them together, but improving maybe their features to some extent and so on. But there are lots of similar smartphones there. And not just devices, just like hardware, but their operating system was adapted to those devices. and it's both built out of some components and composed for different purposes. So we actually might think of components that are adapted, not general, just general generic components, totally generic components, just for all purposes, but within a certain line of products, a product line. This makes sense. And then, what actually becomes the key challenge is how, because there's a great variability of those components, their features and everything. The key challenge that we need to face is how to regulate that variability. And this is actually the key to use. Let's look at this process. Now that there was a slide before that, but I don't know, I think it's not at the moment important. We might get back to it if I would be feeling that something is missing. But this is a scheme, an older scheme from the past century that actually depicts the process of reuse based on what I just, on this principle of regulating variability. And it is denoted here as domain engineering and application engineering, but practically another expression for this is software product lines. The process actually enables you to have some kind of a planned and controlled development of generic components for a particular context. And you go, as you would go through the phases of software development, through analysis, design, and implementation, but it's not just, and it does not mean that you cannot iterate, of course. It does not need to be a strict waterfall, but it's just to depict the main flow. So, because in the end, you don't want to end up with analysis results, you want to end up with implementations, something that works. So, the difference is that it is not that you are analyzing the problem from a specific problem, but you go one level above to get a bigger picture of the whole domain. What is a domain? Well, you define that. But if it is too big, too general, then you will end up with developing with an overkill. You can't manage that. So, some banking systems, but maybe particular kind of banking systems, some academic information systems, maybe for not for all universities. E-shop systems are quite generic, but that might be yet another domain suitable for applying this process called domain engineering. In the end, the domain implementation, it's not depicted there, but yeah, it is. Well, the most prominent result of this are some kind of components. What are components? We talked about this. These need not be just closed boxes that you just connect through particular points or wires and so on, connectors, but they might be, even if we don't speak, if we forget completely about aspect orientation, frameworks. Frameworks are actually the most common form of components. and they are not strictly they are not defined on an input-output basis. So we actually end up with some software that is not yet put together to work together for a particular purpose. It might contain different other different results. We talked here about how to compose aspects. David talked about this. I destroyed that scheme there. Something like just-in-time compilation. Actually, and the parser builder, again, the pattern that is for the purposes of to be used. You are not going to develop, strictly speaking, a parser for some language, but you might do so. So even such kinds of artifacts are produced in order to make your way through that domain. And sometimes you generate even particular languages called domain-specific languages that are very limited, but enable you to express what you need very efficiently. And all this enters this process of application engineering, where you would actually imagine this process mostly like putting together components, but that's not the only thing. You actually need to know the customer needs. You need to perform some kind of requirement analysis based on those needs, and you need to do some design and analysis, and to integrate and test your components and so on. So it might not be that straightforward. It depends on how composable are your components and everything. Not everything will be ideal, so there's some adaptation or something. It's dropped from this custom development, custom design. So it's difficult to embrace everything in this domain engineering process. So you will need to adapt as you go by producing with the production of an actual product. And how you go about those requirements, and how you go about this putting together things, and how they're related, well, that's that variability that I mentioned. So you need to identify your features. Some features need each other, some features are exclusive, some are alternative, and so on. So you need to build a particular variability model. So this is actually the idea that is being applied consciously or unconsciously in numerous ways in software development, today's software development, mostly unconsciously, and it doesn't go really, as I said, strictly that you need to develop all the components, everything you can imagine, and just then put them together. So it's not that clean. It's a dirty world of software development. So and dirty money is involved there, or money. So you need to think in terms of money, and that's what is missing from that scheme, which is mostly and the notion of domain engineering most predominantly used in Europe, whereas in United States they use the software product lines. So instead of thinking about the product lines, production of products, and how to get money out of that, and how not to end up with no money. So you need to invest though in the beginning somehow. So you might decide, well, if you would decide to go just for this approach, then you would need to invest quite a lot, some few years of development and lots of money, and no products until you develop all the components. So that is completely new product line, and you go revolutionary. So you just jump into this, and it's the most risky way to go with this approach. Typically, what you do is it's a more opportunistic strategy, or quite an opportunistic strategy to go with existing things that you have. So you develop several systems, and you start catching up similarities. And you see that you're reusing some parts, but you need to adapt them manually. So you start thinking about parameterizing some things and making them more generic and reusable to the extent that you need that. So you do the existing things and maybe some more a little bit, and gradually you start building your product line asset that you can use them to build further products. Further requirements will come from in this scheme. It's observable from actual products that you and actual requirements that you receive from customers, and you should feed this back into your domain engineering process in order to cover such components as well, such cases. For the purposes of describing variability, this kind of notation was invented. It's more an academic endeavor, but some kind of spreadsheets at least, or something like that, you can imagine that you can actually also use them to maintain, at least to maintain the relationships between features. It's probably not that obvious as in such diagrams, but then again these diagrams can grow and become very big, but you can separate them and reference each other as needed in other diagrams. Now the key idea is that you have some features that are inevitable, that are mandatory, like like this is our account example. Actually, we had that code. If you recall, let me just remind you of this. This is an example from AspectJ in action. We had this mentioned in one of the prior lectures. That this is a kind of a toy. Our toy account with explicitly stated balance and account number, and we have those operations, so debit and credit. And what we did here for the purposes of demonstrating aspects was setting up a minimum balance rule. Virtually, this is a kind of a feature that we need to implement or have in our system. And when we think of that, sometimes we need it and sometimes we don't. So our minimum balance rule is an optional feature. So this anti-circle means optional features. Account, maybe even account type is an optional feature. We might distinguish between account types maybe for some very simple banking purposes. We might not, but all the times we want to have account number. So the granularity of features, as you see, might be very different. So I intentionally went down all the way down to a simple attribute, and maybe checking account, savings account, these alternative features will call for, and that's how it is implemented in code. You can see here, call for inheritance for whole classes. So typically when you have alternatives, you might go for classes. And sometimes those optional features might be very good implemented by aspects. This is also some kind of smaller scale components, and actually you can separate your business rules into features and compose them using aspects. This is what we actually observed, but we haven't talked yet about, we didn't talk about that about software product lines at that moment. Before we arrive to the code that we need to produce, we often use several notations of modeling. How to go about variability on model level beyond that feature model? The feature model is intended to be used to configure other models. So you select the features, and if your model is connected to other artifacts that are actually being represented by those features, which need not be consecutive artifacts, just called units, but might be several, might be spread or might cross-cut several other code units, so some typical lines of code. With aspects, you can separate them into consecutive code units. You actually, by selecting features, you're turning on and off these parts of your application code. And there are systems that enable this in some way or another, and pure variance is a system that does this directly with code, different languages, and it's a commercially available tool. I must admit I did not study to what extent this tool is practical. How widespread it is in practice, but there are many of the systems, but this is available, you can buy it, and there is a community edition as well, and somehow they must get their money. I don't know how it's financing this, but there are lots of and this is quite closed for the eyes of the public. There are in-house custom tools for handling variability, and they are not publicly available. Motorola had some things, and there are some reports on this, but typically you can't get that much details. The principle is the same. So, but back to this question on model level. When we are talking about models here, probably we would think about Steam UML, or that would come to our mind, which we mentioned before. And if we connect to this perspective to selecting, clearly we can use our variability model, which is called feature model. So this is what we saw was feature modeling. To select components that are to be composed, and then the composed model can be generated. It did not talk talk about this actually, maybe I mentioned that you actually can generate when you imagine your themes. Maybe some example there. No, I don't have it. Never mind. Well, I just wanted to mention that then you can based on the rules that are imposed by those themes and the expressions that you have there, it is you can devise the complete design. Typically, you do not do that the same for the same reasons that you do not do this with code. You do this with code. You compose the aspects with the base code or with each other if that's symmetric aspect-oriented programming situation. You compose them only for the purposes to have a complete application for to be executed, and not to read that code and check it whether it's composed correctly. It would be again an overkill to do this. So the same with models. So typically we do not want to see our composed model, but it can be done. There is an approach to aspect-oriented model-driven software product line engineering. I'm not going to talk about that, but I'm just mentioning that this has been explored to some extent. So there are some references to this lecture. You can have a look based on similar things. What we might think of when we talk about aspects, so I'm jumping again into the realm of code, but again I will relate this to the theme approach, is that we do not maybe specifically think of a product line, but in connection or network of organizations, there are such relationships that one organization develops some kind of a generic application. So it's not kind of a developing components so that you get them and you put them together to your application, but an overall application which works is produced, and then in one version, then another version, and you buy it and you use it. But typically, that one size does not fit all, and you need to adapt it to your context. So you customize your application. So I'm talking about the process that probably you're familiar with that notion, customization. Well, it's understandable, but it's a widespread notion because this happens very often. That you have applications that any open source application can be customized, but there is this kind of a typical business relationship that you have some kind of application that you bought, and you are receiving updates all the time, but you need to adapt it to your context, and you have your few programmers that do this. And those poor programmers then are condemned to keep track, or if they do not think about that at the moment of that they are making the changes, even to extract the changes from the prior version and apply them to the new version. This is a kind of use, and we might even relate this. I'm not going to do this, but you might think of this even as some kind of a product line. maybe even like product lines or the domain engineering approach you might think of that as symmetric aspect oriented or related to symmetric aspect oriented programming, and this is kind of an asymmetric aspect oriented asymmetric aspect oriented programming, because you are actually dealing not with equally perceived elements and composing them according to some rules, but you have some kind of your base code, and you apply changes in order to come to the version of the code that you need to. And exactly this is where you can apply aspects in the sense of asymmetric aspect oriented programming, and you can extract those changes into aspects. And I was playing a little bit with this thought throughout several papers that you can see, not directly attached to this, but actually attached to this lecture in a bundle on my habilitation thesis. So this is not meant, all of those things are not meant for you to read them, but you might like to have a look. And the approach has several stages and resonated throughout several years. So we can work with those changes as particular and generic and in one way and specific features like this. Typically you start with some kind of change request. So you need to do something. It might come bundled with, a few things might be composed within the same change request. So you first thing to do is to decompose it into something more, say so, elementary. So here we have the administrator should be able to block and unblock an account from the account view in our banking system, for example. So these actually can be decomposed into these two sub-change requests. One is the administrator can block and unblock an account from the accounts view, and the other is that the user cannot log in if her account is blocked, which is a little bit it's unsaid here in this text, but semantically we can decouple these two. This is not actually very interesting. Only at this moment, from the perspective of aspects, only at this moment we come to aspects. And if we are not very good at aspect-oriented programming, if we don't have particular expertise, even if we do, we might wonder when we are faced with such requests how to actually implement this. And there is a way to help people go through this, because different changes share essential properties, forming change types, consequently. And as I mentioned, there's this specific part, and there's a generic part, and we can observe this happening both at specification and implementation level. Those maybe surprisingly, those implementation change types are actually quite generic. There's not much different, not many different things you can do with code when you think of it. But you can specify that in natural language in the context of a specific problem in an infinite number of ways. So specification change types are related to particular domain, and we can form. How can you help is that you actually go a little bit higher than the specific problem change requests are expressed, and express typical changes in that domain in a little bit more generalized way, and you tie them to particular implementation schemes, and that's it. So actually I have this process here mentioned, but I'm not going to bother you with anymore with this, but I just want to show that this can be related to also to graphical modeling, graphical software modeling, in terms of the theme approach, which might be useful maybe for communicating design decisions, or maybe to document your solutions when you're publishing them somewhere, to make them more visible. As I said, I just want to mention that this is possible. I'm not going to elaborate this in detail in order not to take too much of your time, but we go all the way from the theme top analysis to theme UML. So we start. This is a typical basic view of themes here expressed, where we actually have our requirement, and this is a requirement. This is a specific requirement, and we have our themes that express different parts of the system. One is that there is a login in your system, and another one is that check user is blocked. That you need to check whether user is blocked and allow or not allow them to log in. As you know, you can go to the cross-cutting view, which makes this more obvious, and then you see that you have here your aspect theme, and you go to your catalog where the change types are cataloged in a similar manner. So, but they're not that specific. There is a requirement to introduce additional constraint on fields, and this is a quite general thing in applicable to many different applications. You go about it by typically you have involved a validation form, and then you actually need to introduce additional constraint on fields in that form. Going to the cross-cutting view, it looks like this, and hopefully looking at such schemes, you might observe the similarity. I'm not talking about graphical constellation or the setting of the elements, but semantic similarity between these, and taking into account that your application actually has some validation forms and everything. You actually map these two, and you might now pick a particular change type catalog this way for the implementation. Then you actually have this elaborated as a theme UML cross-cutting aspect theme like this, and then you actually use this theme as a template to develop a specific theme. I know it's not very readable, but I'm just talking about and illustrating the idea. So go into comparing these two, we'll need more time. But the general idea is that you can actually visualize this approach. You apply your aspect, of course, using binding, and you come to an aspect-oriented solution which you implement in your aspect-oriented language, maybe in aspect J or some other, and that's how you go with changes. So eventually you will end up with a system with a huge number of changes implemented in this way, and that might be a kind of a problem in its own right. So that's a disadvantage of this approach, of course. But then again, when some changes become more stable or whatever, you can what it's called, that process. We have aspect-oriented. When we are taking out aspects out of object-oriented code, we are actually not changing how that code actually behaves. We are doing some kind of refactoring. Refactoring is that notion. Yeah, so this is the opposite direction. So you maybe noticed, and maybe even in some other courses you heard maybe by Professor Polashek about aspect-oriented refactorization. So this would be the opposite process where you have your aspects, but you want to get rid of them, so you do. You need to put them into your common object-oriented code back. If you compare this to, if you think further, what comes to my mind, a similar process is so-called denormalization or relational databases. So you are normalizing them in order to make them more maintainable, but eventually that becomes an overkill, and that becomes maybe from the point of view of effectiveness or efficiency, it becomes a problem. So you need to put that to a lower level. So, how about use cases? Typically, what is related to this, and we know, is the extended relationship to these changes. So we could go with this even if think about this design even using use cases. So we need not go for in practice very uncommon theme approach, but we also have peer use cases which actually are a setting for symmetric aspect-oriented programming. We might think that that decoupling by use cases. Actually, there are two things to say about this more further than we talked before. One is displayed here, but another one that maybe I should have mentioned before is that we could think of those use cases and aspects in such a way that we could actually implement use cases, separate use case logic into aspects. you can imagine that to some extent. I will relate this also to this approach, which is mentioned here, and sounds something maybe not really relevant to aspect-oriented software development: data, context, and interaction. This is an approach developed by Trygve Renskag and Jim Coplin, and is strongly proposed by them as an approach to go with I don't know, for development of common information systems, at least. This approach decouples the stable part of the architecture from its variable part. We are again at the question of variability, or the notion of variability, but maybe in a little bit different way. Why is this being done? Because the stable part, or maybe mandatory part in terms of feature modeling, the stable part actually is something that we can do once and reuse as such, but we have different use cases, and new use cases typically are coming to us via further change request even. And we need then to be flexible with how we operate. This will remain, so the business remains the same. We have those accounts and everything, and typically there are transactions actually which are being recorded in the accounts, and which is was not shown correctly in that example that I displayed. So the business typically does not change that much, although there might be some changes. But what changes are those use cases, and use cases are actually something that can be or needs to be, and they are performed. The results of use cases need to be transferred into this part, this stable part. I mean, it's stable as a scheme, but there are variables, there are attributes, and everything that changes. These are domain objects, and what you do in your use cases, you do your calculation, and you go to this level of transferring the results to this level of typically implemented as some kind of dumb objects, not very smart objects, only set and get methods or something like that. And how to connect these two parts? Well, there are different opinions and ways to go with this, depending on the programming language. But one way, although Jim Coplin is not a big fan of aspect-oriented programming, one way to go is with aspect-oriented programming. In more dynamic programming languages than AspectJ is, it's a statically typed compiled programming language. You can go with more flexible binding mechanisms that will bind the roles that are set in use cases to the actual objects, which are not very smart, as I said, which just record or carry the data. And then, when you are finished, you can unbind them. You can't really do this binding and unbinding in AspectJ that easily, or maybe at all. So that's a disadvantage. But you can decouple the two levels, and maybe I even have something there. Or maybe if you get back to this, even to this account, where is it? It's too far away. The account example, you can see that there is a there are some kind of a mask for some method. This is not an aspect. This is an aspect. Okay, so we are putting there what we need into the count. The count acts more like that domain object, and this aspect actually implements some kind of part of a use case. And maybe actually the code that I wanted to show, or which would be more appropriate, is the way how we actually implement themes. So you have that example with what was it? We had with reordering. Not reordering methods. What was that example? I had before some graphical objects, but now I can't remember. Where we had that constellation of an abstract aspect and a concrete aspect, which is devised from it, and there was an abstract point cut. This is the typical way that you use to implement themes. Themes are actually, when you think of them more deeply, quite related to use cases. So you might even think of themes as use cases, and that generic way of expressing what needs to be done, and then specifying it further in that concrete aspect. This is the way to go with maybe with this connection that we need to maintain for the purposes of decoupling use cases from domain objects. I shouldn't have done this. Okay, so and then if you do this right, then the underlying architecture of your system would be capable of taking use cases just like as if you are putting them on a thread like this, and you don't have to mess with the thread itself too much, at least, hopefully. So you're putting, and if you want your use case out, then you can take it out. And again, you can base your variability model on whether use cases are present or not. Some use cases are needed in some applications, and some are not. So this is a kind of a way to think of why we are decoupling use cases from the basic architecture. Well, yeah. And that's what this is. Know your slides before you use them. Actually, I knew that I expected this, but elsewhere, and then I was in a doubt that actually somehow that I maybe dropped this. This is the way of implementing themes that we talked about before. So this is that abstract aspect, and what is interesting here that you can introduce you can introduce interfaces inside your aspects, and then use them as roles. Use cases, as you know, are based on roles. So you have roles. Some roles are explicitly stated, most notably the system role and the actor role, human actor role. But if you decouple that system role a bit, typically in your sequence diagram, or you come to a set of roles that are that are interacting within that use case, and you don't want those roles to be you need to write at least part of your code, your use case code, or as much as you can, like this, relying on those roles. But what are those roles actually? It will be defined only when you bind them to the domain objects, and you bind them in that devised aspect like this, using this declare parents construct. And that's it. I mean that data context interaction approach is interesting in its own right, beyond what aspect-oriented programming has to do with it. So you might like to have a look. There's a bunch of references. One of them is the book on lean architecture, and even if you don't buy that data context interaction approach, half of the book is devoted to quite general wisdom of software development. So I highly recommend that book. Now, what we talked about here, or mainly me, or just me, was regulating variability within a domain as an effective way of achieving software usability. We saw that aspect-oriented feature implementation can help in this, to make features pluggable, like that minimum bounds rule. And use cases are, despite you might hear more and more about user stories now, these days, use cases are still with us, and I think that don't buy that hype with user stories, or call them user stories, but think of them as use cases as much as you can. And use cases can be actually preserved more or less using aspect-oriented programming. In maybe there are even several ways of doing this, depending on what aspect-oriented programming language you use. And then in Aspect J, for sure, we have that ability to more to work with asymmetric approach. So extended relationship is viable, and we can mimic a little bit of symmetric aspect-oriented programming there as well. So for peer use cases. Questions? Comments? Questions or comments? Okay, so then, as I said, we may stop here, and we'll have another set of seminars, another presentations, so one seminar with several presentations, three presentations. Next week, I'm not here, so you don't have to come here either. But I will have a look at your tests and provide the solution and so on, so that you don't have to worry about the results, about the grades, or anything that comes to your mind, because we will lose another week for consultations and for everything. Anything that you struggle with in your projects, or you would like to my comment on that, or whatever, write me an email.
If I may ask, do you know any like real-world examples of when you are actually using aspect-oriented programming for use cases? I mean, like where they are, I mean, like big corporations or like medium-sized corporations that actually have a core and then like add functionality to aspect-oriented programming.
I don't know about that. To be honest, I don't know about that, and it's just like with feature modeling. It was invented in 1990 by Kyo Kang. He invented it while visiting Software Engineering Institute. So Software Engineering Institute, you might probably have heard of it, is quite an influential organization with respect to software development, and that feature modeling it was not, and some years after that, some I don't know, 10, 15 years after that, or no, 20 years after. I'm not sure about the date of the publication, but there was a study that uncovered that actually that particular notation of feature modeling is not used in practice at all.
Of course.
At all.
Okay.
Yeah. So just like with this, yeah. Well, I'll make my point very quickly. But just like as I said, there's much more to feature modeling than that particular notation, and you have to deal with your variability in one way or another. And the same holds for aspects and for aspects and use cases. If somebody is using aspect-oriented programming, chances are high that they are using that in a way that is close to preserving use cases to some extent, but probably I would be surprised that somebody does this consciously. That they are talking about, okay, we would like to preserve our use cases. Maybe they are not even writing their use cases, or chances are that they write their use cases somehow, and then they start programming and the use cases are drawn away. So, but the short answer would be I don't know. So maybe I didn't have to explain this that much in order to satisfy your curiosity. Yeah.
Thank you. Because I was just thinking that where actually in practice would I use it? Like I'm going to program something or to engineer something. And why would I go with this approach? Opposed to
that I can talk about that for about an hour. But actually, I can make it a quick explanation in some 15-20 minutes. Just talking. Use cases are not that uncommon as aspects, and preserving use cases in your code would help you with dealing with change requests which are coming all the time, and you need to change things in your code, but your change requests talk in your use case language, not in your code language. And if use cases are dissolved all around different parts of code, I don't want to say components, then you have to look for those places. Even if you know where they are, you have to get to them, open the files and change everything. And it's not kind of in one place. And if it would be, then it would save you much of the time. If it would be there, then it would save you much more time in adding new use cases and everything, and it has a pleasant consequence of not polluting your basic architecture, your domain model with use case related variable or unstable things.
Okay, and then the other question is like, where is the line, where is the core system, and where are the, like you, because you know, like the core system also consists of some use cases, like, I don't know, you have 12 use cases which are covered by the core system, and then like you would use aspects only to add another, like use cases and functionality.
Well, I don't know whether there is a core system.
Okay.
Whether that core system that I'm talking about, whether you would think of use cases on that level. Those use cases would be very primitive use cases. Actually, in that, if you recall that scheme, Alistair Coburn proposed that metaphor, C metaphor. So they will be quite deep in that C, and those use cases will be more like CRUD use cases: create, read, update, delete. Not very interesting use cases.
Okay.
Yeah, so those more sophisticated use cases, which are concerned with user perspective, they are actually operating with typically with several those entities in the domain model.
Okay.
And
okay, that makes sense. Thank you.
Any other question? Okay. Thank you for your attention. And as you know, this was the last lecture, so I won't bother you anymore with this or like this.